This episode is sponsored by Audible. Ever since humans figured out that the sun is powered by hydrogen fusion, we've imagined controlling the process and powering our civilization with miniature suns. But as it turns out, the sun is highly impractical, and we're going to need to design something a lot better. So today we are looking at fusion power, how it might work, what's holding up this technology, and what cool new options it opens up for our civilization. Many of these possibilities are less obvious than simply cheap electricity or fast spaceships, but just as important. This is a topic we mention in passing a lot on this channel, as a keystone for many of our future technologies and pathways, so as we progress, I'll pop up the cover art for the relevant episodes. I thought we should start by addressing the challenges with achieving a working fusion reactor. There is an overused saying that makes me scowl whenever I hear it, that fusion is the technology of 20 years from now, and always will be. Fusion as a serious concept is a lot newer than many of our other power sources, and has progressed neither particularly faster nor slower than most of them. Just an example, solar power, itself an example of harnessing fusion from the sun, has only recently become economically viable as a primary power source. Back when I was a kid in the 1980s, we really only saw photovoltaics on very low-energy, portable devices like calculators, as it was very expensive and inefficient. It was not new technology then either. Way back in 1876, it was found that you could generate electricity by exposing selenium to sunlight, and Charles Fritz made the first solar cells in 1883. So it took over a century before we even had good enough solar to consider commercial usage of it. It was also half a century after those first solar cells before we even knew what fusion was. And before that, we thought the sunlight running those primitive solar cells was caused by gravitational collapse. We had our first working artificial fusion source a mere generation later, with the hydrogen bomb in 1952. Similarly, while Ben Franklin did his famous kite flying experiment with electricity in 1752, it was half a century later before Alessandro Volta, for whom the Volt is named, built the first electric battery. Then it was a couple more generations before we saw the first electric generators and engines, and a couple more before Edison and Tesla hit the scene. Considering how hard it is to experiment with fusion, something which only naturally occurs in the heart of stars, it isn't all that surprising that we still don't have a working fusion reactor less than a century after we even realized such a thing as fusion existed. It's not helpful when folks go around talking about 20 years from now like that was useful or meaningful, when its timeline is still shorter than the development of many other technologies, from computers and rockets to other power generation mechanisms. The other big issue is that you need large, high-tech, and expensive facilities just to experiment with fusion in a serious way, which usually means anytime you learn something new from an experiment, you need around 20 years just to digest and theorize about that new data, draw up a new experiment, pitch a grant proposal for major government funding to build new massive and expensive facilities, and then build them, before you can get your next set of data to refine your models, rinse and repeat. Now as to the mechanism, there's a bit more to it than hydrogen slamming together and turning into helium at millions of degrees. At high temperatures, the electrons get stripped off atoms and you have a plasma of atomic nuclei. In the case of common hydrogen-1, the nucleus is just a single proton with no neutrons. To fuse two protons together, you first have to overcome the repulsion of their positive charges, and the closer you get them together, the greater the force and energy involved. That energy is what we call the Coulomb barrier. The normal means for supplying that energy to move the particles together at high speed can be done in a particle collider, but the method used in stars is just heat, which is just a measure of how fast individual particles are traveling. One of the things that slowed us down on figuring out what powered the sun was that its temperature isn't actually high enough to overcome that Coulomb barrier. that takes various quantum effects, and so does binding the protons together once they get there. And here's where we get into what makes hydrogen fusion so tricky. It's a hurdle that comes early in a fairly complicated process. When a pair of protons get close enough together, the strong nuclear force will bind them, kind of, into a very unstable isotope called a diproton, which nearly always splits right back into a pair of protons. Very rarely, and here's where quantum mechanics comes in, that diproton instead emits a positron and decays into a nucleus of deuterium, a proton-neutron pair. From there are actually a number of next steps that might take place, some of which is the deuteron might fuse with another proton or deuteron to produce various intermediate isotopes that undergo fusion and decay reactions of their own, before finally producing nice stable nuclei of helium-4, which have 2 neutrons and 2 protons. But the difficult hurdle to clear, the bottleneck in the whole process, is that rare decay of a diproton into deuterium. That bottleneck is the reason stars take billions of years to use up their hydrogen. The half-life of a proton in the core of our Sun before it is fused into deuterium is about 1 billion years, which is to say, bouncing around at that temperature in the core where fusion is actually taking place, any given proton only has coin flip odds of fusing into deuterium in 1 billion years, even though it would fuse briefly into diprotons several times along the way. That's a good thing for us because we wouldn't be around if the Sun burned fuel faster than that. Indeed, bigger stars create a higher pressure at their cores, resulting in faster fusion, so they have shorter lives precisely because they have more fuel. Even then, it's pretty slow for our purposes. It doesn't come up much in our discussion of fusion as a power source, but if you could replicate the conditions inside the Sun in some reactor down here on Earth, with several tons of fusion fuel inside it, that would release perhaps 1 billion joules of energy over the course of 1 billion years, which means it could run a light bulb. And while it would last 1 billion years, you'd have to expend energy to maintain and run the thing too. That's the 2 foremost challenges of fusion reactors: getting a net positive energy gain, and dealing with all the damage to the components and containment vessel from the radiation. Fortunately, the past few decades of research have yielded improvements in the efficiency of the design and durability of the alloys we use in fusion R&D, though still not enough. But again, such a reactor doesn't interest us much as a power source, any more than an H-bomb does, so we need something that can run a lot hotter. People talk about how hard it is to replicate the conditions inside a star, but we are way past that. We usually estimate the temperature of the Sun's core at about 15 million Kelvin, while those Tokamak fusion reactors you've heard about can run at 150 million Kelvin, 10 times hotter, and we've actually briefly produced temperatures in the trillions in labs by ramming particles together. So again, we are not trying to replicate the center of our Sun, because that's not good enough. We are also not trying to do proton-proton fusion much right now. The default approach is to use deuterium or tritium, hydrogen isotopes with a proton and 1 or 2 neutrons, or helium-3 with 2 protons and 1 neutron, or lithium which has 3 protons. These isotopes have lower Coulomb barriers to overcome to produce a fused particle and release energy, so they are our first step. Deuterium-deuterium, or DD fusion, is often seen as the most attractive because deuterium, while rare compared to normal hydrogen, is still very common on Earth, whereas tritium has a half-life not much over a decade, so it's hard to find, and helium is quite rare on Earth, and helium-3 even more so. Handily, if you do have a fusion reactor, you can build ships that can quite quickly and economically go fetch these rare fuels from our various gas giants, and helium-3 is an attractive fusion fuel for reasons we'll get to in a bit. Remember how difficult it is to produce deuterium from protons. When we fuel a fusion bomb or reactor with deuterium, we are taking advantage of the fact that dead stars, of whose material our planet is made, already took care of the most difficult part of fusion for us. Thanks, universe. Your ideal fusion reactor, though, would run basic hydrogen all the way through the various heavier fusion chains to iron, releasing energy at each step. This series of reactions can be considered the ultimate goal, as it's the most efficient use of fuel, but achieving such a thing is a long way off. I should note that not all fusion reactions produce energy. In general, those resulting in elements heavier than iron are net negatives. These reactions are easier in some ways too. It's fusion when you add neutrons to uranium-238 to turn it into plutonium-239, for instance. So regular fusion is hard to do, particularly as we have to do it better than stars can, and with far less mass and gravity to work with. So what are the methods? Well, first, there is the H-bomb, which uses a fission explosion to make fusion occur in much the same way we use conventional explosives to set off the fission reaction. We can make power with this, and I mean usefully too. You can make small fuel pellets of plutonium and your fusion fuel, essentially small H-bombs, and set them off in something that can absorb the energy, like water or preferably molten salt, which you then tap for power more slowly using conventional heat engines like many power plants use. Then all you have to do is set a new one off every so often to reheat the liquid medium. This is a fission-fusion hybrid, arguably a chemical fission-fusion hybrid, since it uses chemical explosives to ignite the fission to ignite the fusion. But bomb-grade explosives aren't cheap, and neither is weapons-grade uranium or plutonium for the fission, or deuterium and tritium for the fusion, at least the tritium anyway. Deuterium actually is relatively cheap, and more so when you have an abundant cheap power source for separating it from water. So it's pricey, but the cost would get lower with scale. These need to be big plants, and the bigger the better. Ideally one's powerful enough you only needed a few per country, but at least it lets you get a lot more juice out of your fissile materials. Whether or not it would be competitive or cheaper than existing power is debatable, but that wouldn't necessarily matter if you're running out of material for those existing sources. Now you could make smaller bombs for smaller reactors using transuranic elements beyond even plutonium, but that wouldn't be for Earth-based power, but some place where you needed a small and short-lived but powerful reactor. These aren't high-tech futuristic technology, incidentally. I'd say we could build one tomorrow, but the scale of such a plant would imply many years of construction to make something big enough and shielded enough to absorb even small blasts. However, this sort of approach is more attractive if you've got cheap superconductors, since it means you can have very few but very large plants, or ones in isolated areas, without losing lots of your energy to resistance in your electric wires. Of course, superconductors also make awesome magnets, which is the keystone of the best known approach to fusion, tokamaks and other magnetic confinement systems. Hot hydrogen and helium turned into plasmas are charged particles, so very susceptible to magnetic fields, and so we can use them to contain our plasma. This is important because that plasma needs to be hundreds of millions of degrees, and even our best alloys can only handle thousands of degrees, so if the plasma could touch the containment vessel, it would slag the whole thing. Your basic tokamak is a big toroid, or donut, created by using magnets to contain the plasmas, and to exert the force on them to speed up and start slamming particles around so they get hotter. The primary problem is that doing this takes energy, hence the concept of break-even. So you need a reactor that produces more energy than it takes to heat everything up. The next problem is actually utilizing that energy, and the general assumption is that you'd be absorbing the radiation given off as heat in the containment vessel, and exchanging it with coolant, with which you'd then generate power through a normal heat engine. There's a lot of losses in such a process, which means your real break-even, in a practical engineering and economic sense, is even higher. The next problem after that is that you are irradiating that containment vessel. You have to if you want to get power after all, and while magnets are good at containing protons and electrons, they don't protect against gamma rays, neutrinos, or neutrons, all of which are being produced, though the neutrons are the major concern. None of these are thought to be unconquerable problems, and we've been slowly approaching the break-even point over the years, but we've also been encountering other issues as we progress. The Tokamak tends to be the default fusion reactor everything else gets compared to, and comes in other shapes than toroids, like spheres, but it isn't the only approach. Even focusing only on magnetic confinement, there are many other variations. Another method is inertial confinement, which usually uses a laser or charged matter beam to slam enough energy into a fusion fuel pellet to ignite fusion, and is conceptually pretty similar to the technique we discussed for making Kugelblitz black holes, only a lot easier. This is the approach the National Ignition Facility uses. Another confinement approach is inertial electrostatic, which uses electric fields to speed up the plasma rather than magnets, though the Poylwell approach combines the two. You've also got magnetic and electric pinch approaches. A pinch in this context is where you get some electric filament, such as a plasma, and compress it magnetically, and you actually see this in the sky a lot with lightning bolts and the aurora. There's a few types of pinch designs, but the main one is the Z-pinch, which you might recognize from the Z machine, or Z Pulsed Power Facility at Sandia National Labs. This is also an example of pulsed power, same as the H-bomb route, where the idea is to produce it in quick enough bursts that it's essentially continuous for practical applications. There are many other methods, but I'd like to get onto the practical impact of fusion, so we'll skip them, though I don't want to imply their omission reflects badly on them. While the idea of cold fusion has a deservedly shady reputation, a lot of other fusion experiments get tainted by association with that, usually unfairly. The last thing I wanted to mention real quick is helium-3 and aneutronic fusion. Most fusion approaches produce a lot of neutrons which damage and irradiate things, and we don't want that if we can avoid it. Helium-3 produces a lot less neutrons in its various fusion chains like helium-helium, helium-deuterium, or helium-lithium. It's harder to do than various deuterium and tritium reactions, but it would permit longer-lived and lighter reactors, which makes it especially tempting for spaceship engines. There is very little helium-3 on Earth, and the Moon isn't really a great source of it either, due to its very low concentration in the regolith. But there is plenty of it out in the gas giants, and that could easily drive colonization of Uranus and Neptune, as we discussed in Colonizing Neptune, as they have the highest concentrations and plenty of deuterium too. The key thing is you don't need much of it on the Earth or the Moon to start using it, since the moment you have a fusion reactor good enough for a spaceship, you've got a spaceship that can easily run back and forth to Neptune to collect helium-3, and a reactor that can easily power refineries and habitats around those gas giants, far from the sun. Indeed, it's good enough for interstellar travel too, potentially allowing speeds of 10 to 20% of light speed, though more realistically, probably less than that. Check out Atomic Rockets if you want a detailed breakdown of the various hypothetical fusion drives. Winchell's website goes into the details without bogging it down in technospeak. Obviously, the biggest application for fusion, normal or aneutronic, is power generation, since down on Earth you don't care about power to mass ratios. Fusion rockets are the other, as we just mentioned, but it's not so good for ground-to-space ships, because while you can accelerate slowly in space, which fusion is really good at, you really need high thrust to get out of an atmosphere, and your default high-efficiency, high-power fusion torch drive does not radiate its containment vessel to warm it up and run a heat engine or superheat some propellant, but rather it dumps all that hot plasma out the back as the propellant, which is decidedly unhealthy. Not that standing in a normal rocket flame is very healthy either, but a super hot plasma exhaust with lots of gamma rays and neutron flux is a whole new level of hazardous, especially considering such ships probably need to be quite large too. They also might not be great for power generation in space, at least not reasonably near the sun. Fundamentally, while fusion is very energy dense, fusion power is really not. You're heating something up to run a normal heat engine, and in space you could achieve the same thing by taking a bunch of thin parabolic mirrors and aiming them at some working medium. Considering how cheap a mirror is, how much sunlight there is, and how much empty space there is to put the mirrors in, you are probably going to find it's cheaper in the inner solar system, in terms of both money and mass for stationary power generation to just use solar. Though as with every power generation method, there's likely to be occasions where one system outperforms another for a specific use, even if in most other cases it does not. Now down on Earth, what's the advantage? First, you're not beaming any energy down from space, as we discussed in power satellites, or dealing with clouds or nighttime for ground-based solar. Second, even if you are limited to deuterium or even helium-3 and tritium, you're going to get a lot more energy from those stockpiles on Earth or throughout the solar system than you would from chemical or fission fuels. There's no such thing as a truly renewable power source, but we count the sun as the next best thing, and fusion parallels or beats that. It also doesn't generate the highly radioactive waste that fission does, though I should note that the fear of radioactive waste from fission, especially with modern methods, is decidedly exaggerated. It also doesn't produce carbon dioxide, nor does extracting deuterium from ocean water cause any ecological issues associated to mining. In fact, since carbon dioxide from fossil fuels is produced by adding oxygen to hydrocarbons and producing water and carbon and energy, it's worth noting that you can run that process backwards, just paying energy to do it. That's not advanced science. Sucking carbon dioxide and water out of air to make hydrocarbons and oxygen in reverse is quite easy. It's just going to take you more energy than you get by burning it. But if you've got a huge source of energy, though not a mobile one, you suddenly can start making gasoline out of air as a nice compact, carbon-neutral power source. Chemical fuels are awesome ways of generating power compared to even our best modern batteries. So if you can synthetically produce a cheap, unlimited, and ecologically safe supply of them, the impact would be huge. It could be carbon negative too, since you could dump that carbon out of the air into mine shafts or maybe make diamonds or graphene out of it. Needless to say, those are valuable to us too, but diamonds might be energy prohibitive to mass produce as a construction material, unless you have good fusion reactors. There's also aluminum though, and for that matter steel. Aluminum is awesome stuff for building many things, but cost prohibitive because it takes a ton of electricity to make. Similarly, while you do need carbon for steel, the main use of it in steelmaking is for heat, so fusion lets you make both cheaper then. And if you are using it to run carbon sinks, it lets you get away with using concrete to your heart's content without carbon concerns. It also makes vertical farming, or cold climate farming in greenhouses, economically viable, as you can now run lighting and heating at competitive costs to natural open-air farming, amplifying the amount of food you can get out of a chunk of land. You can also desalinate water and pump it anywhere with that kind of energy, allowing the conversion of arid deserts and tundras for agriculture. Similarly, with cheap power, you can recycle virtually any material economically and extract new metals in more environmentally friendly ways. We're only touching on the options available, which we've discussed in a lot of our episodes, particularly the Impact of Fusion episode in our show's first season, and the Arcologies and Econopolis episodes that looked how far you can go with vertical farming when you have a ton of cheap energy. This is a power source that basically eliminates most ecological problems, directly or indirectly, allows interplanetary and even interstellar space travel, and lets you terraform planets or build and light and heat artificial habitats. I think sometimes the skepticism toward fusion, as mentioned at the beginning, has to do not with it developing particularly more slowly than most other technologies have, but rather, in part from its breakthrough and wonder status, it being seemingly miraculous. Now there are still some downsides and limits. First off, the cost of power is not just the cost of fuel, which is not free even for fusion, especially if you need to use rarer isotopes than deuterium or plain hydrogen. Power plants need maintenance, electric grids need maintenance, but you'd expect to see a big drop in cost, and possibly more of a subscription approach, rather than a per-unit approach like we tend to do with phones and the internet. You pay for access to a certain amount of power whether you use it or not, rather than per unit of energy, which might mean big industrial users get their energy very cheaply, as everyone's really paying for their electric lines and building and maintaining the power plant. You'd also have huge knock-on effects to the economy when gasoline, fertilizer, construction material, and many manufactured goods all get cheaper. The price of power might only get cut in half, but if everyone is earning twice as much and paying half as much for many goods, it's not just a tiny cut in your electric bill. It's an economic snowball, and it's why I usually count fusion as one of the handful of technologies that if you've got it, either by itself or maybe with one other, instantly kicks you into a post-scarcity civilization. Putting it bluntly, within a couple of decades of us developing a viable commercial fusion reactor, even one that can only match modern energy costs, whether that be tomorrow or a century from now, will almost certainly push humanity into an era of universal prosperity, since so much of what's holding us back from that today is the limited stockpiles of fuels and the worries over their usages. Of course, it's not a total end to ecological worries like global warming either. Greenhouse gases trap heat, but if you're using enough power, green or not, you can start warming up. Fortunately, you need to have trillions of people living on Earth before that was a serious issue, and we discussed some ways to get around that in Ecomonopolis's planet-wide cities. One of those approaches was great big space towers or orbital rings for radiating heat, or bringing food and materials down to Earth cheaply, so you could reduce how much heat you made here on the ground. And active support structures, which require a lot of power, is something fusion is great for too. And that's fusion in a nutshell. Unsurprisingly, the power of the sun, when we get it working, offers us a very bright future. Fusion is one of those technologies, like smart automation, that offers a key to unlock the galaxy to us and make our own world into a paradise. Many authors tend to write dystopian science fiction to add tension and challenge, but while those often make for great stories, they often feel very unrealistic to me, even if they have good hard science in them. There is more to realistic science fiction than just getting the science part right. The civilizations on display have to feel realistic for the setting and technology too, and of course paradise is rarely without its own new challenges, and can be a bit subjective. One of my favorite authors in that regard is Peter F. Hamilton, particularly his Commonwealth saga, beginning with the novel Pandora's Star. Set in the 24th century, the book shows us many fantastic and immense ideas, but also gives us a close look at day-to-day life and how those wonders, like energy and land abundance and life extension, begin shaping that civilization. Later books in the series follow that civilization into future centuries. The series is also narrated by John Lee, who, as I've mentioned before, is my favorite audiobook narrator, and as usual he gives an excellent performance that only improves an already excellent series. You can get a free copy of Pandora's Star at audible.com/Isaac, or text Isaac to 500-500. Audible offers a 30-day free trial, but each month you're a member, you now get a free audiobook and 2 Audible originals, and those credits roll over to the next month or year and stay yours, along with any books you got, even if you later discontinue your membership. And with their convenient app, you can listen on any of your devices and seamlessly pick up where you left off, whether you're listening at home, commuting, running errands, or off jogging or at the gym. Audible makes it cheap and easy to access a vast collection of amazing stories. So a couple quick announcements before we hop into the schedule for the rest of the month. First, an update and apology. Back around the beginning of the year, I grabbed a post office box after requests I'd give folks a non-electronic way to send me things, and obviously didn't want my home address up there on the internet. But some confusion during the setup resulted in a lot of that getting returned to sender, and I didn't find out for months. That should be fixed now, and the address is still Isaac Arthur at P.O. Box 529, Geneva, Ohio 44041 in the United States. Second, we have a new extra episode up on Nebula about the butterfly effect, and I'll leave the promo link in the episode description so you can use the 7-day free trial to check that out, and our previous one, the Paperclip Maximizer. Nebula is a new streaming service a bunch of us creators got together to make as an experimental alternative hosting platform to give us more flexibility in content and control of our content, and its launch exceeded even our most optimistic expectations. There's a lot of material I and other creators on YouTube mostly don't create because we worry about getting punished by the recommendation algorithms, and Nebula is designed to help us with that, and will keep adding features as it grows. In general, the stuff I upload there that is just bonus episodes will migrate over to YouTube after a couple of months, but other content like extended commentary or behind the scenes material that folks ask for but which would get butchered by the YouTube algorithms will likely stay exclusively there, and we'll get channel specific links for Patreon supporters integrated into that in the near future too. As you probably noticed, we had a lot more callbacks to prior episodes than normal, as this topic is very integrated into a lot of our episodes, and these days there's about 200 episodes. Many look at things which seem nigh impossible, but technologies like fusion might one day bring them into existence. With that in mind, we'll be having our 200th official episode, Things Which Will Never Exist, in just 2 weeks. Before then though, there's another topic we discuss a lot, and that is megastructures or other giant constructs like generation ships or artificial planets. And something we don't look at much when discussing those is how you go about maintaining those and sweep up all the debris you generally need to clear out or generate in making and using them. So next week, we'll take a look at the untidy underside of our big bright future in space janitors and megastructural maintenance. For alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, hit the like button and share it with others. Also, if you want to check out any of those mini past episodes we mentioned today, check out the playlist for the channel here on YouTube or our website isaacarthur.net. Until next time, thanks for watching and have a great week.